In this video, we're going to look over the answers for the 25th of March, which we learn about our sugars. So first, we're going to have to do some memorization, just like we did for our amino acids and our nucleotides. Now, the body doesn't use that many different types of sugars, but I would like you to know the sugars that we have boxes for here. Know their name and their structure. So on the test, you're going to see a structure, and I'm going to ask you for a name. I'm not going to give you the name and ask you to draw the structure, but you should be able to look at the structure and recognize it for the sugars that are listed. Now, our first question has to do with stereoisomers. A stereoisomer is a molecule that differs at one chiral center. So if we look at our ketopentoses, keto has a ketone, pentose means 5 carbons. We only have 2 chiral centers. And the way you do this math is that at each chiral center you can be either L or D. There's 2 possibilities. So the total number of stereoisomers are 2 chiral centers raised to the power of, 2 possibilities raised to the power of 2 chiral centers equals 4 different stereoisomers. If you go to a ketohexose, we have 1, 2, 3, 4, 5, 6 carbons. So that's 2 raised to the power of 3, which is 8. And a heptose would be 7 carbons. 2 raised to the power of 4, which is 16. Right, so continuing on with epimers, some true and false, looking at our sugars here. So if we look at sorbose and psychose, are these epimers of each other? So we're looking at our chiral centers, and an epimer means that you are different at exactly one chiral center. So the first chiral center is the same. The second chiral center is different. They're on different sides. The third chiral center is the same. That means that these 2 sugars are indeed epimers. Now let's look at sorbose and fructose. First epimer, different. Second epimer, different. So these are not epimers of each other because they are different at more than one chiral center. If you look at erythros and arabinose, so here is arabinose and erythros is up here. So we have different numbers of carbons, so they can't be epimers. So you need the same number of carbons. How about D and L fructose? So D and L fructose cannot be epimers of each other. And what constitutes a D sugar versus an L sugar? I should state that. So to get a D sugar, you are looking at the chiral carbon that is furthest away from your C double bond O. If it's on the right side, it is D. If it's on the left side, it is L. You can see that all the sugars in our body are D. All of the OHs that are furthest away from the C double bond O are on the right side. So what if we had L fructose? You might think it's true because if it's L, that means this chiral center, the farthest away, the one that I'm highlighting, would be on the left. But if you switch this chiral center to L, for it to still remain fructose, this chiral center right here would also switch. This chiral center right here would also switch. Otherwise, it would not be fructose. The reason why this is fructose is because the first chiral center next to the C double bond O is different from the other 2 chiral centers. And it's D because this chiral center, the furthest away from the C double bond O, is on the right hand side. If this was L, everything would flip, so they are not epimers. Now we have arabinose and ribulose. Well, they're different types of sugars, different numbers of chiral centers, so they cannot. Or sorry, I was looking at ribulose. I wanted arabinose and ribose. So chiral center, different, same, same. So they are. Now ribose and ribulose, that's what I wanted to talk about when I was saying that you have a different number of chiral centers, so they cannot be epimers of each other. So this is not a question, so I meant to take this out, but go to your lecture video to get an explanation on this slide. So question 3, draw the furanose and pyranose forms of ribose. So a puron has 1, 2, 3, 4, 5 carbons in the ring, and a furan has 1, 2, 3, 4. And so we're looking at ribose. And what happens when your linear sugar cyclizes is that the OH molecule will attack the carbonyl carbon, and you're going to form a ring structure. And every time you see that oxygen in your ring, it used to be an alcohol OH. So you're looking to draw a carbon or a ribose with a 1, 2, 3, 4, 5 carbon ring, and the way to get a 5 carbon ring for ribose is if the very last OH attacked our C double bond O. While if you have the furan form, 1, 2, 3, 4 carbons, that means your last chiral carbon, there we go, your last chiral carbon attacked your C double bond O to make 1, 2, 3, 4 carbons in the ring. Alpha beta sugar. So to be able to answer what an alpha beta sugar is, we have to understand what are ring sugar, some terminology. All right, and there's a special carbon in all of these rings, and it's called the anomeric carbon. Your anomeric carbon is the carbon that used to be part of the C double bond O. That's called an anomeric carbon. And on a ring, you can always find the anomeric carbon because it is the only carbon directly attached to 2 oxygens. So what I'm highlighting right now is the 2 oxygens attached to my carbon. What I'm circling is my anomeric carbon. That used to be my carbonyl carbon. All right. So once we have that, we can start talking about what is alpha and beta. So an alpha sugar is you find your carbonyl carbon and you find what direction the OH is pointing. So here the OH is pointing down. If your CH2OH group is pointing the opposite direction of the ring, that's called an alpha sugar. So OH pointing down, CH2OH pointing up, alpha. While on the other case, so let's find our anomeric carbon. It's right here because we have an oxygen. The OH is pointing up. The CH2OH is pointing up. Both are pointing at the same direction, so that's beta. Same thing in C, pointing up, while in D, OH pointing down, CH2OH pointing up, so that's alpha.